Welcome back, guys, to another video on types of chemical reactions. In this one, we are going to focus on single replacement, also known as single displacement. It just really depends on the literature you're referring to, but they pretty much mean the same thing. Now, let's look at the definition. Single replacement occurs when an element reacts with a compound and replaces another element in the compound. So that's a little bit confusing. So let's look at the example we have on screen. We are saying that we are going to start with an element by itself and a compound. Now, during the reaction, the element will ideally replace one of the elements that is part of that compound. So we would end up with a new compound, and one of the elements that was originally in the compound in the scenario B would be by itself as a product. Now let's look at some actual elements because this A, B, C can get confusing. So let's say that we are starting with sodium. So sodium is an element. Yes, there's two of them, but that's because it's balanced. But sodium is an element, and iron 2 chloride is a compound. So we are starting with an element and a compound. Now what is going to happen here is that during the chemical reaction, the sodium will come in and kick off iron from the compound and displace it. So we literally mean there will be one replacement, single replacement reactions. The name tells you what it does. So the result is going to be sodium and chlorine now being in a compound and iron being by itself. So in a way, all you're doing is switching our elements here. Now, something important to note is that metals will replace metals and non-metals will replace non-metals. So what I have here on screen, the one that is single, the element that is unbonded, that is not part of a compound, and here I'm talking about sodium, Na, is a metal. So when we're writing down our chemical reactions, we need to identify if the element that is by itself, right, if it's a metal or a non-metal. Because if it's a metal, the one that it will replace will be the metal. If it had been a non-metal, it would have replaced chlorine, but that's not the case here. So now let's talk about the reactivity series. Another word for that would be just simply activity series. Now, why does it have two different names? Well, activity series is a more common way that it's referred to. Now, the reason it goes into that is because it talks about how some metals will actually interact and displace some other metals who are bonded. Why is it called reactivity? Because it is based on the reactivity trend on the periodic table. Now, as the definition here on the first bullet point on screen says, it is used to determine if a reaction will take place. Now, when we were talking in a previous couple of minutes ago, when we're talking about the single unbonded element coming in and replacing the element inside of the compound, well, not every single time that will actually happen. And depending on which one is more reactive, we will determine if we have a chemical reaction. Now, reaction is based on the differences, again, of the reactivity of the metals or non-metals involved. So that's a lot of information, and we need to look at examples to really understand this. So here, what you have on screen is a copy of the STAR reference sheet that we have here and that we use in class. Now, here on the right side, we have this section that says increasing activity. It's circled in red. That is really where we are focusing our attention on, okay? So make sure that we have a copy of this or we are able to refer to it while we go through the example. Now, the important big idea for activity series that we need to keep in mind is the following. Metals of higher reactivity will displace less reactive metals involved in a bond, meaning a metal of higher, right, because this is increasing, so a metal on the top will displace a metal lower than itself. Okay, so if the metal is not higher, then there will be no reaction. So let's look at these two examples that we have on screen. Magnesium plus silver nitrate. Let's find magnesium on the activity series. Magnesium is located right there. Now, the question is, will magnesium be able to displace silver? And why am I focusing on single? Again, because metals displace metals, non-metals displace non-metals. So, magnesium's a metal and silver is a metal. So we're dealing with those two. Now let's talk about this. Will magnesium displace silver, Ag? Well, we will only displace less reactive metals. So the question is magnesium stronger than silver to displace it? Yes, the answer is yes. Magnesium is able to remove silver. So what we will do is we will flip these two elements. So now we will have magnesium, NO3 plus silver. And of course, we always need to make sure that we balance. Question, why did I write parentheses and a 2 for a subscript? Well, because magnesium is a +2 and nitrate is a -1. And of course, we need 2 of them to make them equal to 0 because this is an ionic compound. That's background information we need to have already a good understanding of to be able to do the problems that we're working on right now. Let's look at the second example. The question now flips, right? Can silver replace magnesium? So we have them here still, and the answer for this one is no. Silver is lower than magnesium. So for that reason, silver is weaker than magnesium, and for that reason, we will say that there is no reaction. So you will literally write no reaction. So from this point on, we need to understand that not every single reaction that we look at, specifically single replacement, not every single one of them will actually end up in a reaction. Sometimes they won't. And again, we are looking for if the single element is stronger or weaker than the one that is bonded, right? If it's stronger, meaning higher on the reactivity series. If it's higher, it will replace. If it's lower, it will not. Now let's look on the demonstration that I have prepared for you guys so that you guys can see what it would look like in the lab. All right, guys, so in this part of the video, we are going to go over the single replacement reaction. And what I'm going to do here is I'm going to take a well plate that has a total of 12 sections to it. And I will then place some copper as directed, magnesium, and some zinc, okay? And I'll show you guys in just a moment a picture of what it will look like. I will then at that point kind of like cross apply 4 different solutions. Now, in the solutions, we are going to have, of course, bonded ionic compounds. So we're going to start and we're going to have silver nitrate, zinc nitrate, copper nitrate, one of my favorites. I think the color is so pretty, and iron 3 chloride. So what I'm going to do is that I'm going to apply a total of 10 drops into each of them. I will actually do a little bit more for specifically the zinc because the pieces that I selected are a little bit large, so they might not actually be covered, completely submerged with all 10 drops. What I will do then is I'm going to take a picture of it so you guys can see it and post it here on the video right immediately after I pour. Then I'm going to take another picture after 1 minute of the reaction, and then I will take another picture after 2 minutes. And at that time, we'll be able to really see what has taken place. So we want to make sure that we note if the single unbonded metal, these that I just showed you guys, did indeed displace the metal that is present in our solution, just like we have previously learned in the video based on the activity series. So let's go ahead and do that. What I am doing here is that I am applying about 10 drops of each of our solutions. I will then allow it to rest for a couple of minutes. What you guys see here is the reaction itself at 0 minutes, so right after I was done, 1 minute later, and roughly 2 minutes later. Here's what our samples look like at about 2 minutes and 20-ish seconds. I want to do a quick zoom in. Right here we can see that our copper reacted in 2 places, with the silver and with the iron. Our zinc reacted in 3 different places, with the copper, the silver, and the iron. And our magnesium reacted in 3 places, with copper, with silver, and with iron. And I also want to draw your attention, this reaction particularly is still going. Not as fast, but it's still going. This one took quite a few minutes to start reacting, but regardless, we still do see the bubbles there. So there is some reaction happening there. And in my opinion, these two are just so beautiful. I know this one kind of looks a little dirty, but it is a very pretty one. This one completely turned dark, and then this one is pulling the silver out, so I hope you guys can kind of see in the video. But if you look here towards the bottom, you guys will be able to kind of see the silver itself. And actually, if I'm very careful, I can pull it off from the copper. So this right here would be our silver that we are extracting from. There we are. Oh no, it dropped. It's okay. From the silver nitrate that got replaced by the copper, which is, I think, so pretty. Right here, got our silver. And if you notice, it's very faint, but you can kind of see it. The silver and the copper are basically trading places. And if you notice, the solution for copper was it was like blue, so pretty. And it's very faint, you can barely see it. But the solution itself, that originally was silver, right, it was clear, it's giving that like slightly blue tint. I hope you guys can see that. And if I let it sit there and add more silver nitrate, I'll still continue to be able to extract some of that silver from it. Alright guys, I hope you guys enjoyed.